Nanomaterials have been among the most intensively researched topics in science and engineering for more than 3 decades. Their appeal lies in the fact that matter behaves differently at the nanoscale. Surface effects dominate over bulk properties, quantum phenomena emerge, and chemical reactivity can increase dramatically. These features have generated enormous enthusiasm and ambitious promises of technological revolutions. Yet the everyday use of nanomaterials remains far more limited than the scientific literature might suggest. This gap between research output and real-world impact has fueled myths, regulatory challenges, and unresolved health concerns. Among the most famous nanomaterials is graphene, a single layer of carbon atoms arranged in a hexagonal lattice. Graphene is celebrated for its exceptional mechanical strength, high electrical conductivity, thermal conductivity, and optical transparency. In theory, it could transform electronics, energy storage, composites, and biomedical devices. Another well-known class is metal nanoparticles, particularly gold nanoparticles. At the nanoscale, gold exhibits optical and chemical properties entirely different from bulk gold. This enables applications in diagnostics, drug delivery, catalysis, and sensing. Silver nanoparticles are widely studied for their antimicrobial properties. Iron oxide nanoparticles are explored for magnetic resonance imaging and targeted drug delivery. Other important nanomaterials include carbon nanotubes, quantum dots, silica nanoparticles, and polymeric nanocarriers. Each of these has been associated with specific technological promises, ranging from ultra-fast computing and efficient solar cells to personalized medicine. The intense interest in nanomaterials has given rise to several persistent myths. One common myth is that nanomaterials are inherently revolutionary and will inevitably replace existing materials. In reality, many nanomaterials outperform conventional materials only under carefully controlled laboratory conditions. Scaling these properties to industrial manufacturing, long-term use, and diverse environments is far more complex than early studies often imply. Another myth is that nanomaterials are either completely safe or extremely dangerous by default. Public discourse has oscillated between utopian visions and dystopian fears. The truth lies in between. Nanomaterials are not a single category, but a vast family of materials with different shapes, sizes, surface chemistries, and behaviors. Their risks and benefits must be evaluated case by case. A further misconception is that the sheer volume of scientific publications guarantees technological maturity. In practice, many nanomaterial studies are incremental, exploratory, or difficult to reproduce. The transition from proof of concept to reliable, cost-effective, and standardized products is often underestimated. Despite tens of thousands of academic papers, only a relatively small number of nanomaterial-based technologies have reached widespread commercialization. Some successes exist, such as nanoparticles in cosmetics, sunscreens, coatings, and certain medical diagnostics, but these are exceptions rather than the rule. Several factors explain this gap. Scalability is a major challenge. Producing nanomaterials with consistent quality at industrial scale can be expensive and technically demanding. Integration into existing manufacturing processes is another barrier, as industries are often reluctant to redesign established production lines. Economic considerations, including cost-benefit ratios and market demand, further limit adoption. Finally, regulatory uncertainty and concerns about long-term safety slow down investment and commercialization. Health issues related to nanomaterials remain one of the most sensitive topics. Because of their small size, nanoparticles can enter the human body through inhalation, ingestion, or skin contact. They may cross biological barriers, such as cell membranes or even the blood-brain barrier. Some studies suggest that certain nanomaterials can induce oxidative stress, inflammation, or cytotoxic effects, depending on their composition and surface properties. Environmental impacts are also a concern. Nanoparticles released during production, use, or disposal may accumulate in soil or water, potentially affecting microorganisms, plants, and animals. However, toxicological data are often incomplete, and long-term exposure effects are still poorly understood. Importantly, the presence of uncertainty does not imply universal danger. Many nanomaterials appear relatively benign under realistic exposure conditions, but the lack of standardized testing protocols makes risk assessment challenging.